Hi, and welcome to our next session on acquisition functions in Bayesian optimization. So let's remind ourselves of the core idea in Bayesian optimization. So what we want to do is we want to find a trade-off between exploration, so areas that we have not visited yet. So remember our toy example where we pretty much stagnated here in this local minimum. But of course, we also want to exploit, so we want to search around good design points. And the question is how to do this now in a balanced fashion. And the idea is to use, I don't know, I guess it's debatable whether this is the perfect terminology, but I guess the Bayesian is in Bayesian optimization. I guess it makes the most sense if we use something like a Gaussian process to use something like a Bayesian approach, where we build a surrogate model which yields estimates for the posterior mean, but also for the posterior variance. And the reason why we now use this posterior variance is to express some form of confidence and certainty in our prediction, and then bake that into the acquisition function so we can, describe the utility of an unevaluated point by saying it should be low in terms of estimated cost, but it could also be high in terms of estimated uncertainty, because that means we have not really explored any design points in this region around that specific lambda point. And that would be a case here. So at some point, we would like to explore this area and not completely disregard it, although we have only seen very few points in that area. Okay, and I guess I already introduced this a little bit in the sessions before. So in order now to sequentially propose new points, based somehow on a surrogate model, we don't want to just simply use the prediction function of that surrogate model. We want to use something else, but related. And we will denote this here with a U. I guess U for utility. Could have used A for acquisition, I guess, as well. Yeah, and that acquisition function should, I guess, encode exactly the utility of evaluating point here at that place. And there are different options for forming such an acquisition function. Quite a few nowadays. There are quite many different Bayesian optimization versions, and I will go through the, most common three ones here. So PI, LCB, and EI. And I hope I have clearly said that in the example before, where we, locally stagnated here in this local minimum, we simply use the posterior mean as an acquisition function, and we completely ignored uncertainty. We saw that this does not work too well. Okay, let's now start with the first simple alternative acquisition function. So this is the so-called LCB for lower confidence bound, and the name is indeed very suggestive and describes exactly what happens. So our acquisition function is simply the posterior mean minus tau times the posterior standard deviation. What does that mean visually? Well, if we look here, we can see as the dotted, or I guess dashed blue line, we can see the posterior mean of our surrogate model. So maybe this is a Gaussian process. And I've also visually indicated minus tau times the standard deviation. So, and if you now want to have this LCB thing here, this is exactly this, well, it's not the mean, it's the lower bound here of these uncertainty bands around the lower mean, around the posterior mean. And if you look at the formula, you can also see that this rewards regions, if we minimize this, LCB, what we will do, if we minimize C, it rewards regions where this guy here is low, but you get a bonus, so to speak, if this guy here is high, because we put a minus in front of that. And this tau parameter, of course, this should be larger than 0. This controls this mean versus uncertainty trade-off. Unfortunately, this is somewhat of a hyperparameter, so you have to set that, to something like 1 or 2 or something like that. There are also some adaptation schemes, which I will not cover here in this introductory session. And this is a very simple acquisition function. This also doesn't really rely on distributional assumptions. There are also some nice regret bounds for Gaussian process-based things together with, I don't know, upper confidence bound or lower confidence bound types of acquisitions. You can also do this in bandit settings. And if you want to look into the underlying theory, I've given you a reference here. And sometimes it's called upper confidence bound because sometimes you don't want to minimize costs, but you want to maximize rewards or something like that, especially in these bandit type settings. Well, I guess we can also take a look here at this plot a little bit. So, well, I have some design points here in black, right? I'm fitting my Gaussian process to this. You can see the posterior mean, you can see the posterior uncertainty. You can see how the acquisition function is formed. And here, I'm simply copying over this lower confidence bound thing, which I'm marking very badly, and copying this over here into this extra plot. You can also see now where the proposed point would be at the minimum of this thing. I hope this is understandable. I use tau equals 3 for this specific example here. The second type of acquisition function is called the probability of improvement. Now this is maybe makes stochastically a little bit more sense. So how are we forming that? So how about we now write down that we're interested in, so let's say we are at some point lambda, at some configuration lambda, and y of lambda is the random variable that encodes the distribution of the cost value at configuration lambda. How about we now talk about the probability that this value, this cost value at lambda, is smaller than cost min, and cost min is the best value that we've seen in the archive, right? So we want to look at points lambda, points where we haven't evaluated before, where this probability is very high that it's better than the best value we've seen in the archive, right? That seems to be a reasonable approach. Now, fortunately, we can pretty much directly compute that because, well, we know that this guy here is a 1D Gaussian. Of course, it's from a Gaussian, well, it is potentially from a Gaussian process. I guess this is why Gaussian processes are so popular in Bayesian optimization, because there we would know that, or I guess if we were using a different type of surrogate model, we would have to talk about whether this here holds, but let's assume you're using a GP. Then this thing is a 1D Gaussian, this posterior distribution at lambda, and we know its posterior mean, and we know its posterior standard deviation. So we know the two parameters of this 1D Gaussian, so we know the Gaussian. If we know that Gaussian, we can look at Cmin, but Cmin is simply a value that we can obtain by looking into our archive. It's just the best cost value we have seen in our currently evaluated design points. And if we know Cmin, well, we know where that line here is, and then we can simply compute this probability here. And you can also do this with this little formula here, where this guy here is the standard symbol for the normal CDF. Of course, you can also see from this definition that the probability of improvement doesn't really take the size of the improvement into account, it just looks at how, I don't know, certain we are. We'll see a better value, but maybe this value is only slightly better. But we can guess quite well that it's going to be better. Yeah, maybe we do also want to talk about how much this step forward in terms of optimization progress is, and this would lead us then exactly into expected improvement in the upcoming slides. Because this improvement is not really taken into account in the formula, often the PI proposes points which are, I don't know, a little bit too close to the current Cmin, so you not really get this nice exploration behavior, but more exploitation. It's also fairly simple to compute, derive, show that because that when we are using an interpolating Gaussian process, and that was for now our current assumption, that we're using, I don't know, a noiseless BO variant or noiseless data, and then our Gaussian process would actually interpolate all of our training data, that for such an interpolating Gaussian process, this probability of improvement is exactly 0 at the training points. And now the third type of Third type of acquisition function, the expected improvement, short EI. So, and this is, I guess, by far the most popular version of an acquisition function for BO. So how is that defined? So again, we look at this y of lambda random variable here, which is the posterior distribution at configuration lambda. So that's the point we're interested in, where we kind of want to compute the acquisition value or the utility value. And again, we look at Cmin. Now, it seems to be pretty natural now to form the difference between the two guys, right? Because this difference is exactly the improvement we would make, yeah, if we would evaluate at lambda, right? So we have maybe Cmin is, I don't know, 10. That's the best cost value we have seen. And maybe, I don't know, y of lambda is something like 8. So that's lower than Cmin. So we'd make a progress by 2 units, so to speak, in y space. Now, of course, y is random, right? It's a random variable. It's a deterministic value. So yeah, we now have to potentially take the expected improvement we do when we evaluate it here, where our, I don't know, y of lambda value is this Gaussian 1D random variable. Now, as you can see, we are also doing something additional, and this is that we are not just doing Cmin minus y and then taking the expectation. That would sound very natural, because that here really is the improvement, so to speak. I don't know, we could call that guy here yi of lambda improvement, and this difference, and then takes the expectation of that. Unfortunately, if you would do that, although that seems to be very natural, you can show something very easily, I guess, by just looking at linearity of expectation. So the expectation of I of lambda is simply the expectation of Cmin, well, which is just Cmin, minus the expectation of y of x. Okay, and in terms of optimization, we can completely forget about that, because that's constant. And this thing here is just that. That's f hat of x, right? So if I would maximize this bad version of expected improvement, so to speak, I could also just simply minimize this thing. This thing is the posterior mean. And we looked at that, and we already figured out that that's a bad idea, because that really doesn't reward exploration. So this is what we don't do, or why we don't do that. And this is why we do this clipping at 0 here in the formula. Let me just remove all of my little notes. So this is why we do this clipping at 0 here. So we take the expectation, but before we do this, we assume that improvements are always positive. This is, of course, an unrealistic assumption. Yes? We just pretend that, I don't know, cost deterioration, so to speak, that we can also become worse when we evaluate at a point. Of course, especially stochastically, is never the case. Yeah? And for that reason, we clip it at 0, and so we can never get negative improvements. We can only get positive ones. So what we now do is we again look at this tail here. Well, I guess I'm marking this wrong. Well, we look at Cmin, and then we look at this tail here of the distribution, but we now not compute the probability in this tail, we compute the expectation. And this is, again, I hope you agree with me, pretty simple, because this is a 1D Gaussian. And in a certain sense, it becomes even nicer, because if you look at this posterior distribution and you now compute this expectation of this clipped value in this tail, you can very, very easily show that you can get an analytic formula now for expected improvement, which I've put here also on the slide, obviously. I'm not going to read it out. I guess you can see this for yourself. Let's check that we understand all of the elements there. So that's the Cmin, we have discussed that. That's the posterior mean. That's the posterior standard deviation. And this is simply the density and the CDF of a standard normal. And again, this is I'm not joking, it's a nice little exercise for students to show that this analytic formula is actually correct. And you can do that by starting from this thing here and then simply doing a little bit of partial integration on the 1D Gaussian. That shouldn't be too hard. And then you can show yourself that this is indeed true. And again, you can also reason a little bit about this thing and then show that for an interpolating GP at design points, this acquisition function value is also exactly 0. So we're never assuming that anything better happens by evaluating a point twice that we have already evaluated, which I guess for a noiseless scenario makes a lot of sense. Okay, after the horrible formulas, a little bit more visualization. So how about we look at our toy example? And now we use expected improvement and see what happens there. So maybe after these 5 design points, we are in the first iteration, and you can see here how the expected improvement looks like. And this peaks on a, I don't know, I'm not sure whether we should say it's a super unexplored region. It's somewhat close to an already observed design point. In any case, we would now evaluate there. If we do a couple of evaluations, you can see that we also seem to explore here this local minimum. And this is the exploitation property of the thing. You can also see that apparently we begin to, so I've skipped a couple of iterations here. So you also see that we explore the boundaries of the search space. I'm not sure whether I would call that an artifact, but this is something that also happens quite often with expected improvement, that you get very close or exactly on the boundaries because their uncertainty is quite high. But then after a few iterations, here 6, you can see that the actually peaks exactly here in this unexplored region, and which is now, I guess that's an artifact because a 1D function is so simple, which is exactly in the vicinity of our global optimum. You can also see here this remaining peak of activity in this area here of the local minimum, but this becomes, I don't know, lower and lower and vanishes more and more the more we explore this region here, because then posterior uncertainty goes down more and more and more in that region. And at some point it will be so low, the expected improvement will be nearly 0 because we've explored this region so much already. And then we are exploring other regions. Okay, summary and discussion for acquisition functions. So acquisition functions balance exploitation and exploration. Yeah? And usually, nearly always, they do this by somehow combining the posterior mean and the posterior uncertainty of our surrogate model. We have discussed 3 basic types: candidates of acquisition functions, probability of improvement, lower confidence bound, and expected improvement. EI is most standard. I have had very often good success with the lower confidence bound. That also works very well in practice. That expected improvement is so popular is also due to some theoretical properties. And so under some mild conditions, you can actually theoretically show that Bayesian optimization with the GP and EI is a global optimizer, so that it actually converges to the global optimum, or that convergence to the global optimum is guaranteed given an unlimited budget. I guess that's a catch, because we will usually in practice not have an unlimited budget. I guess we'll have quite the opposite. But what that tells you is that the exploration aspect in expected improvement never completely vanishes. So you always have non-zero probability for any region in the configuration space to at some point visit that. And that's not true for all of the other acquisition functions. So for PI, this is not true. For posterior mean, this is certainly not true. And for LCB, it depends on this setting of the tau value. So if this is if this is suboptimal, you also don't get that property. There are many other modern forms of newer acquisition functions. So there are various versions of entropy search, predictive entropy search, max value entropy search. There's the knowledge gradient, Thompson sampling. We'll discuss a little bit later in connection to parallelization. I have linked you a couple of papers. Some of them are not super easy to read. Entropy search, I'm looking at you. If you're interested in these more advanced types of functions, take a look at the references.